Inside a computer, when there's a voltage across a wire and it's carrying an electrical current, this represents the binary digit 1. When there's no voltage across a wire and no current is flowing, this represents the binary digit 0. Logic gates are electronic circuits that manipulate voltages. So in effect, they manipulate the binary 1s and 0s which are moving around inside your computer. Logic gates and the clever ways in which they can be combined together are therefore essential to making a digital computer work. This is ENIAC, which stands for Electronic Numerical Integrator and Computer. It was the first ever electronic general-purpose computer. ENIAC and computers like it had hundreds of valves. A valve is an electric current amplifier. Valves are still used in some guitar amplifiers today because they impart a particular quality to the sound produced. A valve is also a special type of switch. A small electric current flowing through one part of the valve can cause a large current to flow through a different part of it, so the small current is switching on the large current. A valve can therefore be in one of two states, on or off. This means it can represent a 1 or a 0. Although valves were crucial to the development of early electronic computers, there were a number of problems with them. Valves were bulky. They got very hot, which made them slow to switch, and they burned out easily, so they needed to be replaced often. In the 1950s, valves were replaced with transistors. They did the same job as valves, but they were much smaller, smaller than a pea, and they were cooler, faster, and more reliable. Transistors allowed computers to be developed which were much smaller and much more powerful than ever before. This is another type of electronic component known as a resistor. It simply reduces the size of the current flowing through a wire. Now things have moved a long way since the 1950s. It's now possible to manufacture electronic components such as transistors and resistors on a microscopic scale. In fact, the surface of a tiny piece of silicon can contain literally millions of transistors. These days, an integrated circuit the size of your fingernail can have up to 2 billion transistors on it, and at that scale they manipulate individual electrons. This is the symbol electronic engineers use to represent a transistor in a circuit diagram. And this is the symbol used to represent a resistor. If a transistor and two resistors are combined like this, they produce a circuit which behaves in a very special way. This circuit can be represented with its own symbol. It has an input and an output, and it's known as a NOT gate. If a voltage is applied at the input, this represents the number 1, and no voltage results at the output, representing a 0. Alternatively, if no voltage is applied at the input, representing a 0, then a voltage is produced at the output, representing a 1. That's why the NOT gate is sometimes referred to as an inverter. This behavior can be described using something called a truth table. Here we can see if a 0 goes in, a 1 comes out. If a 1 goes in, a 0 comes out. If we combine 2 transistors and 3 resistors like this, we produce another special circuit. This has its own symbol as well, and it's called an AND gate. This time, If we apply no voltage at input A and no voltage at input B, then we have no voltage at the output. In other words, if two zeros go in, 0 comes out. If we apply a voltage at input B, but no voltage at input A, there's no voltage at the output. In other words, a 0 and a 1 going in produce a 0 coming out. If we swap the inputs round, so input A is high and input B is 0, again we get 0 coming out. But if both inputs are high, we have a high output. In other words, if there is a 1 at input A and there is a 1 at input B, we produce a 1 at the output. This behavior can also be described in a truth table. You can see only if A and B are 1 is the output 1. Finally, if we combine 2 transistors and 3 resistors like this, we produce something known as an OR gate. In the case of an OR gate, if both inputs are 0, the output is 0. But if one or the other input is 1, we get a 1 out. Also, if both inputs are 1, we get a 1 out. And here's the truth table which describes the behavior of an OR gate. You can see that only when A and B are both 0 do we get a 0 out. All other combinations of inputs give us a 1 out. To summarize then, these are the 3 main logic gates which you need to know, and the truth tables which describe the way they behave. Later, we'll see how these can be combined to produce some very interesting circuits.